Okay, so the recording is being started, and I just want to make sure that you have a comfortable feeling for this kind of question in section 1.4. So let me give you a moment to copy down this this warm up here, and then we will go over the solution. Okay. Let me just see here. All right. So in this problem, we have three vectors, v1, v2, and v3, that live in three-dimensional space. And we want to know if this set of vectors span R cubed. Okay, now like if you had these vectors, let's say you had these vectors. Let's just take kind of a analogous question here. Okay, so let's say that you had vectors E1, E2, and E3. This is below here now. This is just a discussion. You don't need to copy this below here in the blue. So in our Math 284, we denote these three unit vectors as E1, E2, and E3. In like a physics class or calculus 3, what would those vectors be called? E1, E2, and E3, those vectors. What would we call those vectors? What would we name those? They are basis vectors. That's right, Benjamin. And that's right, Haley. I, J, and K. Unit vectors. That's right, Olivia. And we would call these three vectors here I, J, and K. But in linear algebra, we call those unit vectors E1, E2, and E3. And so do these three vectors here, does the set of vectors given by E1, E2, and E3, does this set of vectors span R cubed? Okay, so I'm getting some very quick yeses there. Benjamin and Haley say very quickly yes, and the answer is yes, because any vector in R cubed in three-dimensional space can be written as a linear combination of these three vectors here. It's easy to see it. Any vector in like for instance the vector 1, 2, 3. Okay, that vector would equal 1 times E1 plus 2 times E2 plus 3 times E3. Okay, any vector in R cubed can be written as a linear combination of the vectors E1, E2, and E3 of that set of vectors. And so that set of vectors, the E1, E2, E3 set of vectors, does span R cubed. And in fact, it's what's called a standard basis for R cubed. And the reason they use this so often is because it's a very easy basis to work with. But remember, it's not the only basis for R cubed. In other words, there are other sets of vectors that also would span R cubed. So up here, we're asking if these three vectors span R cubed. The only thing is, it's not as obvious here with V1 and V2 and V3. It's not obvious if that set of vectors spans R cubed. In other words, I don't know offhand if any vector in R cubed could be written as some linear combination of V1, V2, and V3 vectors. Okay, so that's where we have to put our ideas together to answer the question. So let's go ahead and try to answer the question. So in our solution then, what we'll do is we'll let vector B, which I'll denote with components B1, B2, and B3. I'm going to let that be just some random vector in R cubed. It could be any vector in R cubed. Well, we wish to see if the vector B can be written as a linear combination of V1, V2, and V3. In other words, does x1 times V1 plus x2 times V3 does x1 times vector V1 plus x2 times vector V2 plus x3 times vector V3 equal B? Does that vector equation have a solution for any vector B in R cubed? Okay, that's what we're trying to determine. It was obvious for the standard basis E1, E2, E3, those vectors, that was the case, but we have to formally show it for this set of vectors. Okay, so equivalently, so this here, this of course is a vector equation. Right? This is a vector equation. But the vector equation is equivalent to a matrix equation, AX equals B, if we define the matrix, the column vectors of this matrix A as our vectors V1, V2, and V3, and if we define our vector X as having components X1, X2, and X3. So equivalently, asking to see if the vector equation has a solution, okay, is equivalent to saying, does the matrix equation have a solution? A solution X for any B in R cubed. Okay, please let me know if you have any questions. Okay, so what is the matrix equation then? So you know the well, let me go to the next page so I can show you the matrix equation in concrete form for this example. May I move to the next page? Is anybody still copying this page? Maybe give me a few thumbs up if you're good. All right. Thank you, everybody. Okay. Okay. Excellent. Excellent. Well, all right. So here's AX equals B. Okay. Where we have our V1, our V2, and our V3. And again, that's equivalent by the fact of matrix multiplication. That matrix equation is equivalent to this vector equation. It's equivalent. So the vector equation leads us to the matrix equation. And then the matrix equation, by virtue of multiplying matrices, you know, taking A and multiplying it by the vector X, that leads us then to, well, a system of equations. So you go from the vector equation yields a matrix equation, and the matrix equation yields a system of equations. And this now puts us back in section 1.1 and 1.2. So of course, now we have to determine if this system of equations is consistent. Is it consistent? And indeed it is. So I write out the augmented matrix for the system. And what can you tell me about this system of equations? Well, look at the matrix. Look at the matrix A here. I mean, I want to be a little bit careful how I phrase this, but you know, you have this matrix. Well, I want to be a little bit careful. I want to be a little bit careful how I phrase it. So the matrix A consists. No, I want to be careful how I phrase this. Hold on. The words I have are on the next page. I'm going to go to the next page. But so far, are we okay up to here? Are we all right? Are we all right getting up to this step? Okay, Natalie's good. Ariana's good. Catherine's good. Benjamin's good. Okay. Great. Well, then let's thank you, everybody. Eleanor, Samantha, Louis, Andres, Abby. All right, let's get to the next page then. All right, so then this system of equations is consistent for all B1, B2, B3. What do you notice about the matrix A? If we were to, the matrix A, of course, had the matrix A, I want to say this the right way. The matrix A, this was the second row, but the matrix A originally, if we take the matrix A and interchange the first and second, the first and third rows, we end up with what you have here. Okay, if you take the matrix A, the original matrix A that we had, and interchange the first and third rows, we end up with this. And what does every, well, I want to say this the way I want to say it. If we, there's several ways to look at this, but when I say that the system is consistent, if we think very simply here, the last equation reads 4x3 equals B1, right? I want to be careful how I phrase this here. The very last equation here, okay, the very last equation reads 4 times x3 equals B1. Now, can we solve for x3? Is that like, is x3, no matter what B1 is x3 solvable? Absolutely, because x3 would equal B1 over 4. So yes, so x3 has, no matter what the B1 is, no matter what that value is, x3 can be solved for. Now the second equation reads negative 3x2 plus 2x3 equals B2, right? That's the second equation here. Keep in mind, we know x3 has some value. So given that x3 has some value, will the second equation, negative 3x2 plus 2x3 equals B2, can we solve that for x2? Does x2 have a solution no matter what B2 is? Absolutely. And so we're back substituting, right? It's easy to see. Easy to see. No matter what B2 is, x2 will have a solution. So now you've established that x3 has a solution. Now you've established that x2 has a solution no matter what B2 is. And then the first equation here is negative 3 x1 plus 9x2 minus 6x3 equals B3. And x3 has a solution, x2 has a solution. So will x1 have a solution? I mean, for any B3, does x1 have a solution? Yes, it does. So that means x3, this is x3 has, or x1, sorry, no matter what, for any value of B3, x1 will have a solution. So I don't need to go forth and actually, solve for x1, x2, x3 in terms of the B1, B2, and B3 to answer this question. In my mind, I mean, I can just reason it this way. So indeed, the vectors v1 and v2 and v3 do span R cubed. They do, because there is going to be a solution for all vectors b in R3. And that means any vector b in R3 can be written as a linear combination of the vectors v1, v2, and v3. Okay, does this help you feel comfortable does this help you feel comfortable with this idea? Good. Lewis is good with that. Livia, Abby, wonderful. Ariana, great. Well, let me point something else here out that I also as well on this. So here, the matrix A was, if you, again, take that original matrix A and interchange the first and third rows, you'll get this matrix here. That matrix A, what can you tell me about each column? Maybe I'll put it in black. Each column, well, not matrix A, because the row equivalent form of matrix A, but what can you tell me about each column here? Each column has a pivot. That's right. Good, Lewis. Good, Olivia. Well, actually, I'm not really saying that right. Each row has a pivot. Each row, well, there's a pivot in each row. So in this case, then, the columns of the matrix have to span R cubed by theorem 4. So, there's several ways of looking at this, but I find it easiest to think about thinking about the system's consistent, I find it easiest to just do back substitution. And then it makes me appreciate that, hey, yeah, each row, okay, in the matrix, for that matrix A or the matrix V1, V2, V3, okay, that was, hold on here. Let me say it the right way, the way I want to say it. Yeah, here's where I want to go. This matrix here has a pivot in each row. It has a pivot in each row. Okay, and because of that, the columns of that matrix span R cubed. So, the types of questions that you see, particularly in the multiple choice, like to tie together these kind of ideas. Are there any questions on this? Any questions on this problem? Okay, well, I'll stop the recording.